All right, another video of Chem with Com. We're going to continue chemical equations and chemical reactions. This is part 2 of 4-part series. We're going to start doing molecular equations and net ionic equations, and we're going to explore kind of what reactions are. So when you talk about changes and physical changes, it's taking something and changing its physical state, but keeping the chemical formula the same. Keeping chem formula the same. So imagine ice water, liquid water, and gas water. They're all H2O. Right? So we're keeping the same chemical formula. It has inherently the same building blocks. It just looks different. Same with melted butter or wax, I guess. Butter or wax. Right? You could harden the wax or the butter. You can melt it into something else, but it's liquid and solid. And the physical properties may change. Right? Physical properties are things like density, color, hardness, melting and boiling points, electrical conductivity. It may change when you change physical states, right? But it's not going to change the chemical formula. When we change the chemical formula, we're changing matter into something else, right? So changing matter into something else and changing the chemical formula is a chemical change. So this started off like, this was probably the metal before it started rusting. And then chemically, it turned into this rust. Chromium does not rust, so it has very, very little chances of chemical change, right? Iron can rust, so that shows a chemical change. This is no chemical change because it's just chromium, right? All right, so a few words that indicate chemical changes are rusting. If you hear the word rust, chemical change happened. Burning, there's a chemical combustion. Cooking, same thing. Denaturing, probably. Rotting, decomposition. If you hear those words, you're like, okay, that's a chemical reaction or series of chemical reactions. One of the things we do in lab is we actually visually look for chemical reactions, right? So did a chemical reaction occur? Well, we're doing our experiments. Boom. If we form gas, yeah, chemical change happened. Or sorry, chemical reaction happened and a chemical change. And that the gas could be in the form of bubbles, vapor, odor, like you smell something. It could also have some sort of energy transfer. So that's going to be in the form of light, heat, or cold. Again, we're doing some stuff in lab. All of a sudden we see gas or experience bubbles, vapors, or odor. Cool. A reaction happened. We did a chemical experiment. We saw light, heat, or cold. Boom, that was a chemical reaction. Color change. We did a chemical experiment. We saw the colors change. And so, boom, that's a chemical reaction because what's happening is the atoms are rearranging into new formulas, new chemical formulas. This is a new one we're going to experience here. Precipitate. It's when you have solids forming in various solutions, right? So it's kind of the opposite of dissolving. Imagine you put a teaspoon of salt in a glass and you dissolve it, like you stir it and dissolves. It's actually the opposite. Those salt particles are solid, turning into aqueous. So I'm going to write that here. Chlorine, let's say it's solid. You put it in water, it separates into Na1 plus, and that's aqueous because aqueous means dissolved in water. Chlorine is aqueous, and that's a 1 minus, right? They separate. Well, precipitation is the opposite. They start out separate and they come together and form a solid. And you've seen this in your showers, in your bathrooms, on your sinks. The white buildup, that's a precipitate. That's usually calcium carbonate. All right. Well, We're going to have to build molecular equations to experience and see these chemical reactions, right? Or I guess look at the chemical reactions on paper, right? So this is going to be a lot of review stuff, a lot of stuff from chapter 5. So nomenclature review, go back and take a look at that. Topic 5. Also, we're going to there's some other stuff about chemical symbols, reaction symbols, phases, and stuff like that in chapter 5, and nomenclature stuff, right? So one of the things we really have to remember is we're going to build chemical reactions by, and this is the review part, making neutral compounds. And we'll go over a few of that now. But if you're having issues following along, it's probably because you need some refresher from topic 5. So go back and take a look. Okay. This step here, we'll number them 1, 2, and 3. So step 2, go word by word and write chemical symbols, reaction symbols, phases, and charges. This is a question from the book. All right, we have to build a balanced molecular equation. So let's build that. When carbon dioxide, boom, we got it. This is CO2. Dissolved. If you're dissolving something, that's going to be aqueous. In an aqueous solution of sodium hydroxide. Let's stop there and take a look. We're going to write down chemical symbols, reaction symbols, phases, and charges. So we're doing that. We're writing down carbon dioxide. The way it's named, we know it's CO2. Dissolved means aqueous. Sodium, right? It's Na. We have a predicted charge of 1 plus. Hydroxide is a polyatomic ion that has a predicted charge of 1 minus. All right. The mixture reacts to yield, right? There's a reaction, and the yield is going to be the product stuff, right? If you make a bunch of cupcakes and your yield is 30 cupcakes, those are your products, right? These are the products. Aqueous sodium, we know it's 1 plus. Carbonate is a different polyatomic ion, but it's on your list. It's in the book, right? You should know this. And means plus liquid water. So again, these are our reactants. These are our products. Now let's look here. CO2 aqueous is dissolved in this sodium hydroxide. Now, the neutral compounds is the start of this. Neutral, you cannot do this without neutral compounds. So if we have a 1, I'm going to put it over here. If we have a sodium 1 plus and a hydroxide 1 minus, neutral compounds mean charges add up to 0. Charges add up to 0. That's all we're doing. So if we have a 1 plus and a 1 minus there, the charges add up to 0 with 1 sodium, 1 hydroxide. All right. Cool. Left side's done. Aqueous, because it said it dissolved in aqueous solution. There's 1 sodium and 1 hydroxide because together they make, again, a neutral compound. This is very, very important. All right, next, sodium carbonate. Let's take a look at that. Sodium is a 1 plus. Carbonate is a 2 minus, always. Okay? So if you add those up, that's going to be NaCO3, but it's going to be a 1 minus. We don't want that. We want a neutral compound. So let's try again. CO3, 2 minus. So now we have a 1 plus and a 2 minus. Our objective is to use as many ions as we need to make a balanced, or neutral compound. So now let's add another sodium 1 plus. So now we have the 1 plus, the 1 plus, the 2, that's going to add up to 0. But now we have two sodiums. So it has to be Na2CO3. There has to be two of them because we had to use two to make that neutral compound. So that's going to be Na2CO3. So two sodium 1 pluses and one carbonate 2 minus because together they make a neutral compound. So this is our unbalanced equation. Again, similar to a ingredients list. But we need to balance. That's going to be last subtopic. Right? Count atoms on each side, pick some, start balancing, try it out. How to balance this is just throw a 2 on there. Everything else is balanced. All right. We're not going to go through that because that was last chapter or last topic. So I'll let you go back and review that. So that was, again, that's topic 9, I believe, like part 1. All right, let's continue. We're going to do a practice problem. Let's do it. Write a balanced equation describing each of the following chemical reactions. So solid, again, I'm going to just annotate these words so that we can transform that into a chemical reaction. Chemical reaction, yeah. So solid, sodium chloride, we know sodium's 1 plus, chloride is a 1 minus, is added to aqueous sulfuric acid, hydrogen chloride gas, HCl gas, and aqueous sodium sulfate is SO4, and these are charges of 1 plus 2 minus, are produced. All right. So they're saying this stuff here is the ingredients or the reactants. The stuff here is the product. So let's do that. Remember, neutral compounds, that's what we're doing. So we have NaCl solid, right? Sodium chloride is added to aqueous sulfuric acid. Hydrogen chloride gas and aqueous sodium sulfate are produced. How many do we need of each of these? 1 plus, 2 minus. We need another Na1 plus. So it becomes Na2SO4, and it says aqueous. So that has to be aqueous. All right, let's do, now we have to balance. Inventory on both sides. Since sulfate is the same on both sides, we're going to keep those together. SO4, SO4. We have sodium. We have sodium. We have chlorine. We have chlorine. We have hydrogen. We have hydrogen. Again, we're just doing inventory. Again, we're going to follow the rules in the last subtopic. Sulfate, 1 and 1. Sodium, 1 and 2. Chlorine, we have 1 and 1. Here we have 2 hydrogens right here, and we have 1 hydrogen here. All right, now we have to balance this sucker. All right, I think all we need to do is put a 2 here. Sorry, let's do the thing where you pick this thing with the most atoms. All right, pick the molecule with the most atoms. It's going to be either this one or this one. It doesn't matter. Let's just start over here since it's on the left. All right, H2SO4. So we need SO4s are balanced. We're good. All right, what about hydrogens? We have 2 here, 1 on the right side. So we need to increase the right side, so we put a 2 here. This cancels out. There's now 2 there. And we now have 2 chlorines as well. Now, if you look over here, what's not balanced? Let's pick something else. Well, it's the sodium chloride. Just put a 2 here and we're done. So now we've built an equation and we balanced it. And this takes a lot of practice, and this is a lot of your knowledge from before, so it's hard to start in this chapter. Go back a few, get familiar with this stuff, and then come back and do this if you're having problems, right? All right. Okay, net ionic equations. This is our next topic because we're gonna expand on our knowledge. It's basically where the action is. What um what is participating in the actual reaction? And I'll show you what I mean. So we're going to take this complete balanced molecular equation. We're going to separate these into ions, right? Only things that can be separated into ions, right? Ionic stuff. Ionic is a metal and a non-metal, or polyatomic ions, something with polyatomic ions, right? Metal, non-metal, polyatomic ions, right? Okay. So again, we're going to start with the complete balanced molecular equation, which we just finished. When we separate things, it's going to be a total ionic equation. And then when we get rid of the stuff we don't need, it's going to be now what's called a net ionic equation. All right, let's take a look here. So again, this is the same equation we did from, no, sorry, it's not the same. It's totally different. So, but similar, right? Wait, is that the same carbonic acid? That's this one. So it's this one. It's not the one we did. It's another one. It's the one before that. Okay. So we're gonna remember separate aqueous ionic reactants and products, right? CO2, what you want to do is look at the formula, look at the symbols behind it. Aqueous, cool. Aqueous, cool. Aqueous, cool. We do not separate liquids, so we just don't bother with that. But if you look here, this is not ionic, right? Not because it's not a metal, non-metal, and there aren't polyatomic ions here, right? It's a straight up molecular molecule, covalently bound molecule. So we separate these into different things, right? Na, 2OH. But since there's two, that two has to go to both of those. And we know the charges for sodium, we know the charges for hydroxide. All right, there's two sodiums and polyatomic ions stay together, right? Polyatomic ions stay together. Right? It's very important. Polyatomic ions stay together. All right. So once they stay together, once you separate all these things, right? And the reason why there's not two CO3 is because this 2 for sodium is specifically for that 2. This 3 is specifically for oxygen, but we know carbonate is CO3. Okay. All right. So what we're going to do now is leave out the spectator ions. Spectator ions are exactly the same on the left of the equation in the reactants and in the products on the right side. Exactly. If they're not doing anything and they're the same on both sides, they're not doing anything but watch the other ions work. So we just leave those spectator ions out, and this is the net ionic equation right here. This is where the chemical reaction is happening. All right. The hydroxide's kind of splitting apart. One of them they're becoming water, and the other one's the carbonate's picking up another oxygen, right? Okay, let's try one of these on our own. How many are we doing? We're doing two, looks like. All right. So let's take a look. Diatomic chlorine and sodium hydroxide. So diatomic means two chlorines and sodium hydroxide are commodity chemicals produced in large quantities, along with diatomic hydrogen via the electrolysis of brine. Oh, sorry, are produced in large quantities along with diatomic hydrogen via the electrolysis of brine in water, right? And that's actually supposed to say sodium chloride. Let me fix that. Boop, cancel. Let's just. All right. So sodium chloride is NaCl. It's going to put a little line up here. In water, H2O. All right. If sodium chloride is in water, that's going to be aqueous. Water is a liquid. And they don't actually have the phases here. And I don't know if you're supposed to know this or not, but these are gases. So if you did or did not know, this is always going to be aqueous because it's in water. But let's take a look. All right. So produced in large quantities. These are actually the products. So Cl2 gas plus H2 gas and sodium hydroxide. Right? And this is going to be aqueous. And I think I skipped a step there. Let me back up a bit. I just kind of jumped the gun on that. When it says sodium chloride, right, or sodium hydroxide, we know it's sodium 1 plus, hydroxide 1 minus. So that becomes sodium hydroxide. This sodium chloride should have been sodium 1 plus, chlorine 1 minus, and that makes sodium chloride aqueous, right? So sorry, I jumped the gun there and I kind of did it without explaining myself, but there you go. You have to make the ions first and then you make neutral compounds. All right. Electrolysis of brine, sodium chloride aqueous in water. All right. That's our unbalanced equation. Let's balance it now. NaClHO. NaClHO. All right, here we have one sodium. Here on the right, we have one sodium. One chlorine. Here we have two chlorines. Here we have left two hydrogens, right two hydrogens. Here we have one oxygen and one oxygen. We're almost balanced. Well, let's check it out. Most atoms would be, I guess, water, three of them, or sodium hydroxide. We can do either one. And it all works. Let's do water. Let's do sodium hydroxide. All right. So let's balance the sodiums. Done and done. Let's balance the oxygens now. Done and done. Well, it's getting easy. Oh, sorry, I messed up. Let's redo that. Actually, hydrogens, we have three. Because we forgot about this one, right? So we have one sodium, two chlorines, three hydrogens, one water. So hydrogens are what we're going to balance now. But 1, 2, 3. So we need to get 3 here, but we can't get 3. Let's try. The only way we can do this is by increasing it by 1. So if we're at 1 here, let's cancel that and let me change the pens. I'd say we always have ones there, right? Without a number. So we're going to cross out the 1, and that's going to be now a 2. But now we have 4 hydrogens and 2 waters. Well, how do we do that now? Well, we need to increase the oxygen by 1. So what we have to do is put a 2 here. But now that gives us 2 sodiums, 2 oxygens, but now we have 4 hydrogens, which is good because now we're the same. Look, we have 2 oxygens, we have 4 hydrogens. Now we have to figure the last one out. Well, here we're missing a sodium, missing a chlorine. Here we have a sodium and a chlorine together. We just put a 2 there. Now we are balanced. Everything is balanced. All right, so I'm going to rewrite my equation. 2 NaCl aqueous plus H2H2O liquid, Cl2 gas plus H2 gas plus 2NaOH aqueous. All right. We break apart only the aqueous things. Aqueous and aqueous ionic things. Not just any aqueous things, aqueous ionic things. 2Na1 plus aqueous plus 2Cl1 minus aqueous. Plus, we keep this together because it's a liquid. Liquids do not separate in water. This stays the same, 2 gas plus H2 gas plus, we'll separate this one, 2Na1 plus aqueous plus 2OH1 minus aqueous. This is the balanced molecular equation. This is the total ionic equation. Now what we need to do is let me get a blue pen, is the net ionic. All right, things are exactly the same on both sides. They have to be identical. Those are the only things. Those are the spectator ions. Spectator. We're going to leave them out. We're going to rewrite the equation here. 2Cl1 minus aqueous. Again, spectator ions don't do anything. They're just kind of there, kind of hanging out, like a bunch of lazy bums. But this is where the chemical reaction is at. That's what the total ionic equation is for. It's to showcase the ions or atoms or molecules that are actually participating in the reaction. And it's balanced, so we are all good. So this is the net ionic equation. All right, I think there's one more. Let's do another one. All right. Again, we're going to annotate these words with a bunch of our stuff, right? So again, solid sodium 1 plus, chlorine 1 minus is added to aqueous. Oh, wait, we just do this? Oh, but we're going to now do the net ionic. That's right. Aqueous, H2SO4, HCl gas, and aqueous sodium sulfate are produced. All right, so let's write that out. Neutral compounds. So these are the products, HCl gas, right? And we need two sodiums for this one. So Na2SO4 aqueous. It says NaCl solid plus sulfuric acid aqueous. All right. How we balanced it before, right? And you can go back and check, let's rewind it a couple minutes, is we basically put a 2 here. Now we have 2 sodiums, 2 chlorines. Well, we need 2 sodiums, 2 chlorines, and we have 2 hydrogens in each one. All right, so we're balanced now. Separate all that is aqueous. Let's break those apart now. This you break apart, and this you break apart. Again, this is the balanced molecular equation. We're going to keep this together. 2NaCl solid. Plus, we have 2 hydrogens. We know the charges are 1 plus. Those are aqueous. Plus a single SO4 2 minus, and we know that is aqueous. 2HCl. That's gas, so we don't separate that. This one we do. Sodium sulfate, we have 2 sodium 1 plus aqueous plus a sulfate molecule, sulfate polyatomic ion. That's aqueous. So this is the total ionic equation here. I'm going to box up everything that's the same on both sides. The only one that's the same are these. And again, these are spectator ions, spectator, and they're both, I mean, it's the same thing. So basically the ion was just floating around in the solution. A reaction happened, it's still just floating around. It's not doing anything, right? So those cancel out. We're going to bring that down to make or everything else down to make our total net ionic equation. Plus 2Na1 plus aqueous. This is 2NaCl 2H1 plus aqueous. All right. Well, that is our balanced or net ionic equation. And when it's like this, these cancel out and just become 1. So it's going to be NaCl. I'm not going to test you on that part. I just wanted you to be aware of it. It's not, I don't think it's super important to know that at this point. But we always like to use the lowest numbers possible for pretty much everything. Again, this is our net ionic equation. All right, well, we're getting into chemical reactions, so let's continue on the next video. Thank you very much, and I will catch you next time.